Imagine this. The familiar Duracell batteries, these small cylinders of energy, are the result of a complex high-tech alchemy that began back in the 1920s. Behind their power lie laboratories, zinc, graphite, and a true spirit of endurance. They work in children's toys, medical devices, space programs, and almost never give up first. So what's the secret to making Duracell? I suggest we find out together. The story of Duracell begins not with a bunny commercial, and not even with a shiny copper top cylinder. It was born in a laboratory, in a time when the world had just learned to keep electricity in a pocket. This was back in the 1920s, when a talented chemist named Samuel Rubin and the owner of a small precision equipment company, Philip Mallory, met by chance. This meeting changed the history of household energy forever. Rubin had an inventive zeal. He experimented with new electrolytes, looking for a way to make batteries smaller, more powerful, and more stable. Mallory, on the other hand, had the manufacturing infrastructure, engineering experience, and commercial sense. Together, they created a duo where not only chemistry sparked, but also ideas that worked. Thus, the P.R. Mallory Company was born, which would later become the parent company of Duracell. The real breakthrough came in the 1960s, when the National Aeronautics and Space Administration was preparing for its grand space missions. The agency needed batteries, but not just power cells, but ones that could withstand cold, vibration, vacuum, and years of storage. It was then that Rubin proposed a new type of battery, with an alkaline electrolyte, more stable and longer lasting than traditional zinc-carbon batteries. This technology became the heart of Duracell, whose name originated as a contraction of durable cell. In 1964, the brand was officially named, and over time it became synonymous with reliability worldwide. But a battery isn't just about what's inside. Duracell also created a visual symbol, a copper top and a black body, which in themselves look like power. And of course, the Duracell bunny, which appeared in a commercial in 1973, made the battery a true rock star among power sources. This pink drummer could work longer than anyone else, and became the personification of energy that never runs out. Over the decades, Duracell changed owners. First, it was bought by Gillette. Then the company went to Procter & Gamble, and in 2016, it was acquired by none other than Warren Buffett, the investment genius, through his corporation Berkshire Hathaway. Buffett explained, "Batteries are a business that will never go out of style." And he was right. Today, Duracell is one of the leaders in the global battery market. Its cells power everything, from a TV remote to a pacemaker, from a tourist's flashlight to a space instrument. In each of them lies nearly a century of engineering experience, laboratory work, and real-world testing. Duracell is not just a source of energy. It's a part of everyday life that keeps the world in motion. And it works, and works, and works. It all starts with a cylinder. Not with energy, not with electricity, but with a small steel can, about 1.2 inches tall and about half an inch in diameter if we're talking about a classic AA battery. This cylinder is not just a shell, it's the cathode, the positive electrode that holds all the power inside. The production begins with hundreds of these cans, one after another, racing down a conveyor. First, a paste of manganese dioxide mixed with graphite is pressed into the can under pressure. This mixture is the heart of the cathode. It looks like a dark gray mass that is compacted by presses into a solid crust. It needs to be dense, but not too dry, so that current can flow, but without the risk of leakage. Each battery contains about 8 grams of this paste, and the compaction density is precisely controlled to tenths of a gram. Next, the separator, a thin layer that prevents the cathode and anode from touching each other to avoid a short circuit. This is an extremely thin polymer membrane, less than 1/100th of an inch thick. But despite its thinness, it's strong and porous. It allows ions to migrate, but keeps the masses separate. Now it's the anode's turn. It's made from a zinc gel. No, not solid metal, but a gel-like mixture of powdered zinc with an electrolyte, potassium hydroxide. This paste resembles a thick cream, and its portions are measured precisely to tenths of a gram. It's dispensed from a dispenser and fills the space between the separator and the central axis. A steel pin is inserted into the center of the battery, which serves as the negative pole. It also increases the conductivity and strength of the entire structure. At this stage, the battery is already charged with potential, but not yet ready. It must be sealed. The cell is closed with a sealing gasket and a metal disc. Here, sealing washers made of EPDM rubber are used. This is a type of synthetic rubber that does not let the electrolyte through and can withstand temperatures up to 230 degrees Fahrenheit. The gasket is inserted with micron precision because even a small misalignment and the battery will lose pressure, and with it, its life. The assembled battery is checked. On the line are robotic controllers that check each battery for weight, seal, and voltage. All parameters are read in real time, and if something is wrong, the cell is automatically rejected. There is no room for defects here. Duracell is a brand where every battery must work for months, and sometimes years. I suggest we take a look at the inspection. When a battery is assembled and looks like a Duracell, it doesn't mean it will go out into the world yet. It has to prove it's worthy of wearing the copper top. And this begins with testing. At the factory, batteries move along a special line, fast, straight, and precise, like a military parade. At this stage, each one passes through several automated scanners and sensors. The first test is electrical. A robotic probe touches the battery's poles and reads its voltage in volts, internal resistance, and charge level, all in real time. If a battery outputs, for example, less than 1.5 volts, it's immediately rejected. Because Duracell is not about almost, but about works perfectly. The second test is weight. Too light means not enough zinc gel or paste was added. Too heavy, there might be a problem with the seal. A robot lifts it, weighs it, and compares it to a standard. A deviation of more than 5/100ths of a gram, and the battery is kicked off the conveyor, on the fly. The third is the seal test. This is no longer physical contact, but control using highly sensitive sensors that detect microscopic leaks or pressure drops. Everything happens in a matter of seconds. If a battery leaks even slightly, or isn't sealed tightly, it won't see a store or a device. After testing and marking, the batteries go to the packaging area. There they are fed onto platforms in groups of 4, 8, 12, or more, depending on the packaging format. They are grouped, oriented, and fed to an automatic conveyor that wraps the batteries in blister packaging, heat seals it, and adds a cardboard back with information. Everything that is assembled immediately goes to giant warehouses located right next to the factory. There, dozens of rows of pallets, each with 10,000 batteries. Each pallet is labeled, tracked, has its own batch, production date, and destination. Next, trucks, containers, railways, and sometimes even aviation. The batteries travel around the world, from Texas to Tokyo, from Montreal to Marrakesh. They end up in stores, on Amazon's warehouses, in distribution networks, pharmacies, and sometimes directly in hospitals or military complexes, and only after this, into the hands of someone who will insert the battery into a flashlight, remote, toy, or glucose meter, and it will start to work. After this, the cells are marked. Do you think the text on a battery is just printed? Number. It's a thermal transfer coating that withstands friction, sweat, heat, and even drops. Each battery gets its layer of a copper top ring, then a black body and inscriptions with the name, polarity, and expiration date. At the finish line, packaging. The batteries are grouped, wrapped in blisters, boxes, cases, and prepared for shipment to the world. Production doesn't stop for a second. At just one factory in Bedford, over 2,000 batteries are made every minute. That's over 1 billion batteries a year, and they all go through the same path. From a can, manganese paste, zinc gel, a pin, to the shine that awaits you on the shelf.
Every year, hundreds of power units, bridges, and turbines are built worldwide, but there's one component almost nobody knows exists: How can a piece of metal over 50 feet in diameter be stronger than any welded structure? Why is it forged without a single seam, as if grown from a solid ingot? And how did this technology, created for nuclear reactors, suddenly start transforming wind energy, hydroelectric plants, and even the global heavy forgings market? Stick around till the end. I'll reveal the main secret of this giant ring that even many engineers don't know about.
To really get a sense of the scale here, picture a soccer field. The goal is over 23 feet wide. This ring's diameter, more than double that. You could easily fit multi-story buildings inside it, or a plane. And it's all one solid piece of stainless steel, not a single weld anywhere. In the past, rings this size were made by welding together several large segments. Looked good, but those longitudinal seams always carried a hidden risk. Any micro crack, any welder's mistake, and during an earthquake or under long-term loads, that seam could become the weak point. Chinese metallurgists decided to go a different route. Don't glue it together, grow the ring from a single piece. They used a technique they call additive forging. Here's how it works. Instead of trying to stretch a billet to the right size all at once, they forge it repeatedly in layers, gradually building up and rolling out the metal in the shape of a giant ring. Think of it like rolling out dough and folding it into a log multiple times to make it thick, even, and free of air pockets. Here, instead of dough, it's heated stainless steel and presses exerting thousands of tons of force. First, they melt exceptionally high-grade steel with nickel, chromium, and molybdenum. These additives provide strength, ductility, and corrosion resistance, even in radioactive and high-temperature environments. The resulting ingot looks like a massive metal barrel. It's heated in furnaces where temperatures are many times higher than in a kitchen oven, then transferred to presses. The blank is first flattened, then pierced through, then rolled in a circle, each time rotating and hammering it so the structure becomes as uniform as possible. The incremental forging technique means the metal is constantly built up in the needed direction, while simultaneously being compacted, driving out voids and defects.
With each pass through the press, the ring grows in diameter, but its walls maintain the required thickness, and the steel's grain structure aligns. Engineers constantly monitor temperature, compression force, and deformation rate. If the metal cools too much, it becomes brittle and can crack. If it overheats, the structure flows and the steel loses strength. So the entire operation is run like a complex recipe. Precise steps, holding times, checks at every stage. In the end, you have a solid ring without a single seam. This is critical for a nuclear reactor. The support flange acts like a belt, holding together the vessel walls and all the internal guts, the reactor core, heat exchangers, internal structures. It bears not only 7,000 tons of weight, but also thermal deformations, vibrations, and possible seismic shocks.
Picture the reactor as a massive pressure cooker. This ring? It's the belt that can't budge, not even a micron. No weld seams means way less risk of cracks under cyclic loads, and it makes the whole thing tougher against earthquakes. Of course, forging isn't the end of the story. The ring goes through heat treatment, heated and cooled on a precise schedule to lock in the steel's key properties: yield strength, impact toughness, resistance to creep at high temps. Then come the endless checks: ultrasonic testing for hidden flaws, mechanical tests on samples sliced from machining allowances, hardness measurements around the whole perimeter. Only when engineers are confident the metal behaves identically at every single point does the part get cleared for duty in a nuclear unit.
What's really fascinating is that the breakthrough with this record-breaking ring didn't stay trapped in the nuclear club. The same idea of forging massive solid hoops started spreading to other industries. The hydroturbines at large hydroelectric plants have enormous ring-shaped components that hold the runners and guide vanes. Wind turbine towers need powerful flanges that transfer loads from the blades through the nacelle to the steel column. The fewer welds in these critical parts, the better they handle vibrations and tough operating conditions. Additive forging technology makes it possible to produce large-diameter, solid rings for them that last longer and perform more reliably. The world's most powerful open-die forging presses, including those at China's China Erzong, reach 80,000 tons of force and can deform ingots weighing anywhere from several dozen to over 250 tons, which is exactly what opens the door to forging rings on this scale.
On a global scale, large-scale forgings for the energy sector come from a tight circle of suppliers. Facilities in Japan, China, France, and Russia, each with its own production lines for large reactors, generators, and turbine rotors. Demand for seamless rings isn't just growing in nuclear power. The forged flange market for wind turbines was valued at roughly $1.5 billion in 2023 and could hit around $3 billion by 2032, with seamless ring forgings claiming a significant chunk of that pie. Offshore wind farms need massive flanges and rings that can handle punishing wind loads, salt water, and constant fatigue cycling. Here, seamless rings have a clear edge over welded ones, thanks to lower cracking and deformation risks.
Similar rings show up in hydropower too. Turbine bands, guide vanes, massive flanges for high-pressure pipelines. Anywhere a failed weld could spell disaster, manufacturers switch to giant one-piece forgings. The story of that Chinese ring over 50 feet across, that's just the tip of the iceberg for the entire heavy forging industry. It shows just how far modern blacksmithing has come. Diameters over 50 feet, weights north of 330,000 pounds, design yodes in the thousands of tons, and service lives measured in decades without replacement. And market data for power forgings and wind flanges hints that we'll see more and more of these record-breaking rings in nuclear, hydro, and wind energy every year.
Slam a hammer into your windshield. The glass spiderwebs but holds together, cracks spreading like frozen lightning, yet staying in place. Now hit a side window. It explodes into 10,000 tiny cubes, flying everywhere. Same material, radically different behavior. Every year, factories produce 500 million automotive glass panels worldwide. That transparent barrier between you and highway speeds represents chemistry and physics pushed to extremes. How does molten sand become safety glass? Why does windshield glass behave opposite of side window glass during impact? Stay with us. You'll discover the counterintuitive process where breaking glass makes it stronger, and the shocking secret of the plastic film sandwiched invisibly between windshield layers, the unsung hero preventing decapitation during crashes.
Our story begins not with glass, but with sand. Silica sand mines in places like Missouri and Wisconsin extract incredibly pure quartz, 99.8% silicon dioxide. The purity matters obsessively. Just 0.01% iron content tints glass greenish. Modern automotive glass requires absolute clarity, demanding sand so pure it resembles white powder rather than beach grit. Walk a glass plant raw material yard. Mountains of sand sit beside smaller piles of soda ash, limestone, and dolomite, the recipe unchanged for centuries. Automated systems measure ingredients to within grams per ton. One batch mixer explains, sand is main ingredient, but the additives determine everything: melting temperature, strength, thermal expansion. Get ratios wrong and glass cracks cooling from furnace or shatters first bump on road.
The furnace is where sand dies and glass is born. Temperatures inside reach 2,700 degrees, hot enough to melt steel. The mixture feeds continuously into one end, while molten glass flows out the other. Inside, sand grains disintegrate, their crystalline structure collapsing into amorphous liquid. Silicon, oxygen, sodium, and calcium atoms swirl in chaotic dance, losing all memory of original form. Picture the furnace operation. It runs 24/7 for 15 years straight. Stopping means the furnace cools. Glass solidifies inside, requiring complete demolition and rebuild, costing tens of millions. Operators monitor oxygen levels constantly. Too much air oxidizes refractory bricks lining furnace. Too little, glass contains bubbles. The molten glass glows orange, viscous as honey, ready for shaping.
The float process creates perfectly flat glass, invention revolutionizing industry in 1959. Molten glass at 2000 degrees pours onto molten tin bath. Tin remains liquid at these temperatures, yet denser than glass. The glass literally floats, spreading across tin surface under gravity, achieving perfect flatness naturally. Physics does what human hands never could, create distortion-free sheets. Watch the float bath. The glass ribbon, still glowing red, stretches 300 feet across the tin. Controlled atmosphere prevents oxidation. Rollers pull the glass forward at precise speeds, determining thickness. For automotive glass, thickness reaches 0.18 inches for windshields, slightly thinner for side windows. The glass gradually cools as it travels, solidifying while maintaining molecular randomness. No crystals, no grain structure, pure frozen liquid.
Now comes cutting. The continuous glass ribbon, cooled to room temperature, gets scored by diamond-tipped wheels. The cutting happens fast. Automated systems follow computer patterns, scoring complex windshield shapes in seconds. Pressure applied to scored line causes glass to snap cleanly. Skilled cutters once did this manually, taking minutes per piece. Modern systems process one windshield every 6 seconds. But raw glass is dangerous. Sharp edges could slice arteries. Grinding wheels smooth every edge, creating slight bevel preventing cuts. Then washing. Automotive glass undergoes cleaning process NASA would envy. Deionized water rinses away particles. Even microscopic contamination shows up later. One speck of dust between windshield layers creates bubble visible to driver, requiring part rejection. Cleanliness isn't preference, it's requirement.
Tempering transforms side and rear windows into safety glass through controlled violence. Glass pieces enter furnaces heated to 1,300 degrees, just below melting point. The glass becomes plastic, molecules mobile yet solid. Then comes the quench. Jets blast cold air across both surfaces simultaneously. The outer layers cool and solidify instantly, while interior remains hot. This creates locked-in stress. Outer surfaces compress, while interior stretches, like tightening rubber band inside rigid tube. The tension is enormous. Tempered glass achieves 4 times the strength of regular glass. But here's the crucial part. When stressed beyond limits, that internal tension explodes the glass into thousands of small cubes. The pattern isn't random, it's designed. Those dice-sized pieces have dull edges, reducing laceration injuries. One safety engineer puts it bluntly, tempered glass doesn't cut throats. That's the whole point.
Windshields require a different approach, lamination. 2 glass sheets sandwich a plastic film called PVB, polyvinyl butyrol. This clear film, thinner than credit card, performs miracles during crashes. The glass sheets go through gentle heating, softening slightly. Then into the autoclave, pressure vessel combining heat and pressure. Picture autoclave loading. Workers stack 50 windshields on racks separated by spacers. The door, thick as bank vault, swings closed. Temperature rises to 250 degrees while pressure climbs to 200 psi. Under these conditions, PVB melts slightly, flowing into every microscopic gap between glass and film. Chemical bonds form. After 90 minutes, the layers become inseparable. What exits is single unit, glass-plastic-glass sandwich, impossible to separate without destroying.
The PVB layer's genius reveals itself during impact. When windshield hits something, rock, bird, human head, the glass fractures, but PVB holds fragments in place. The windshield spiderwebs but doesn't collapse. During rollover accidents, that intact windshield prevents roof-crushing occupants. In frontal impacts, it keeps airbag deployment controlled, providing surface for airbag to push against. Modern windshields incorporate additional tech. Acoustic PVB layers dampen road noise. Heated windshields use transparent conductors embedded in glass, microscopic wires invisible to eye, but conducting electricity, melting ice. Some luxury cars use infrared reflective coatings, reducing cabin heat by 40%. That simple windshield contains 7 layers, 2 glass, 3 PVB interlayers, and 2 coatings, each serving specific function.
Safety glass emerged from accidents. In 1903, French chemist Edouard Benedictus accidentally knocked flask off shelf. The glass shattered but held together, coated inside with cellulose nitrate residue. He recognized implications for automobiles. Early windshields were flat plate glass, killing occupants during crashes. But public pressure and regulation forced change. World War II accelerated development. Military needed shatter-resistant cockpit canopies. Post-war, automotive glass became sophisticated. Curved windshields arrived in 50s, requiring precise heating and forming. Tinting followed in 60s. Today's windshields represent billion-dollar research. Material science, chemistry, and engineering converging in that transparent shield you barely notice. Carbon emissions drop 38% using recycled glass versus virgin sand. Industry recycles 12 million tons of automotive glass annually. Processing cullet, recycled glass, requires 25% less energy than melting raw materials. Here's the secret we promised. Windshield and side window behave differently by design. Laminated windshield must hold together. Its job is containment during crash, keeping occupants inside, maintaining structural integrity. Tempered side windows must shatter. Their job is escape. During submersion or fire, occupants need exit path. Tempered glass shatters easily from inside, allowing escape. Wrong glass and wrong location kills people. That difference isn't accident. It's calculated engineering saving lives daily. From sand to safety, the cycle completes. We've learned that best protection sometimes means braking in controlled way. That windshield isn't just keeping wind out. It's a sophisticated safety device engineered through centuries of tragedy and innovation. The glass between you and highway could be all that stands between minor accident and fatal ejection. We barely notice it, which proves it's working exactly as designed. Transparency isn't the achievement. Staying invisible while performing miracles, that's automotive glass mastery.
Hold a car battery. It weighs 40 pounds. 30 of that is pure lead. Every year, humanity produces 11 million tons of this heavy, soft metal. Romans used it for plumbing 2,000 years ago. We banned it from paint and gasoline because it poisons children's brains. Yet we can't quit it. Lead stops X-rays dead, stores electrical energy better than any alternative, and possesses one superpower no other metal can match. How does rock containing lead sulfide become the shields protecting radiologists? Why do we mine fresh ore when mountains of old batteries exist? Stay with us. You'll discover why lead is simultaneously essential and deadly, and the shocking secret making it the most recycled material on Earth. 99% returns to use forever.
Our story begins in Missouri's Lead Belt, America's primary source. Unlike flashy gold mines, lead operations look industrial, almost boring. Massive drills bore 800 feet down, following veins of galena, lead sulfide ore appearing as metallic gray crystals. Each ton of ore contains just 3% lead. The rest is worthless rock requiring removal. Underground, miners work in perpetual darkness, drilling blast holes into rock faces. The lead content makes galena unusually dense. Lift a basketball-sized chunk and it weighs like a bowling ball. You feel lead before you see it, explains one miner. Galena has this heft that surprises you every time. Explosives fracture the ore. Loaders scoop rubble into trucks, climbing back to surface through spiral tunnels taking 20 minutes to traverse.
Topside, the crushing begins. House-sized jaw crushers reduce boulders to gravel, while workers monitor from control rooms behind thick glass. Lead dust is insidious, invisible particles that accumulate in bones, causing damage that appears years later. Modern facilities employ enclosed systems, but older operations tell different stories. Walk through a 1970s lead smelter photograph. Workers in street clothes, no respirators, covered in gray dust. Many develop neurological problems by age 50. The industry learned hard lessons about lead toxicity. Today, air monitoring systems track particle counts continuously. Workers shower before leaving. Clothes stay on site. Blood tests happen monthly. One manager puts it bluntly: respect lead or it destroys you. There's no middle ground.
The ore enters roasting furnaces heated to 1,400 degrees. Here, sulfur burns away as sulfur dioxide, captured and sold to sulfuric acid manufacturers. What remains is lead oxide, a yellow powder looking harmless but deadly if inhaled. The roasting building operates under negative pressure. Air flows inward, never outward, preventing escape of lead-contaminated atmosphere. Watch the roasting process through observation windows. Yellow flames dance over tumbling ore. Operators adjust oxygen flow constantly. Too much air, lead oxidizes excessively. Too little, sulfur remains. Getting it wrong costs millions in lost efficiency. The roasted material, called calcine, moves to smelting via enclosed conveyor belts. Nothing touches open air. The paranoia about containment isn't regulation theater, it's survival. Lead contamination cleanup can bankrupt companies.
Blast furnaces reduce lead oxide to metallic lead through carbon chemistry. Coke, purified coal, burns at 2,000 degrees, creating carbon monoxide that strips oxygen from lead oxide. Liquid lead, melting at just 621 degrees, pools at furnace bottom. Picture the tap. Workers drill through clay plug. Molten lead, silvery and dense, flows into molds, creating 90-pound ingots called pigs. The metal moves like mercury, forming perfect spheres when droplets fall. Lead's density is deceptive. A 5-gallon bucket filled with lead weighs 200 pounds, impossible to lift. Ancient Romans made lead pipes by pouring molten metal into sand molds. The same basic process works today because lead's properties haven't changed in millennia.
Refining removes impurities through clever chemistry. Adding zinc causes copper to rise as dross skimmed off surface. Calcium treatment removes silver. Lead and silver frequently occur together geologically. The final product achieves 99.99% purity. This refined lead feeds manufacturing plants producing batteries, radiation shielding, and specialized applications. But here's where the story shifts. Increasingly, smelters don't process mined ore, they process old batteries. Secondary smelters, as they're called, have grown to dominate the industry. Why mine lead when every dead car battery contains 20 pounds ready for reuse? The economics are brutal. Recycled lead costs 40% less than mined lead. Primary smelters struggle competing. Many shut down, unable to match prices of operations running on discarded batteries.
Battery recycling begins at collection centers, where mechanics and scrappers deliver exhausted batteries by the thousands. Workers drain sulfuric acid into neutralization tanks. Each battery contains about 2 gallons of corrosive liquid that can't enter recycling stream. The acid gets neutralized with lime, creating calcium sulfate, sold as drywall ingredient. Nothing wastes. Drained batteries move to breakers,
rotating drums with internal hammers that shatter cases, separating lead plates from plastic housings. It's violent. The noise resembles continuous demolition. Lead plates sink in water, plastic floats. Simple physics achieves separation. The plastic gets washed, shredded, and sold to manufacturers making new battery cases. The lead plates, still coated with lead oxide from battery chemistry, head to furnaces for smelting. One facility processes 50,000 batteries daily, enough lead to manufacture 12,000 new batteries.
The smelting of recycled lead mirrors primary smelting, but operates at smaller scale with tighter controls. Furnaces melt battery plates at 1,000 degrees. Impurities rise as slag, skimmed continuously. The molten lead flows into casting machines, producing standardized ingots shipped to battery manufacturers. Here's the remarkable part. A battery recycled today will be back in a new battery within 30 days. The loop is that tight. And that battery will get recycled again in 3 years when it fails, and again and again. Lead never wears out. Its atomic structure remains unchanged, regardless of how many times it melts and resolidifies. The lead in your current car battery might have started life in Roman plumbing, been refined into medieval type, reformed into ammunition, and now cycles through automotive batteries. Lead is functionally immortal. Lead's history intertwines with civilization's darkest chapters. Romans sweetened wine with lead acetate, called sugar of lead, not knowing it caused madness in emperors. Medieval alchemists poisoned themselves studying it. The gasoline industry added tetraethyl lead as anti-knock compound in 1921, despite knowing its neurotoxicity. For 50 years, automobile exhaust sprayed lead over every city, poisoning children and causing measurable drops in IQ. The phase-out began in 1970s as evidence became undeniable. Removing lead from gasoline represents public health's greatest victory. Childhood blood lead levels dropped 90%. Paint bans followed. Today, lead use concentrates in batteries, radiation shielding, and specialized industrial applications. We've learned to respect lead's toxicity while exploiting its unique properties. The metal that once poisoned Rome now powers modern transportation, but safely, contained, recycled endlessly.
Carbon emissions dropped 72% producing recycled lead versus mining virgin ore. Industry saves $63 billion annually through battery recycling. Processing scrap uses 65% less energy than conventional smelting. Here's the secret we promised. Lead achieves 99% recycling rates, the highest of any industrial material. That car battery has a 99% chance of being recycled properly because it's worth money. Scrappers pay you for dead batteries. Mechanics collect them religiously. The economic incentive creates a closed loop more efficient than any regulation could mandate. From ancient Rome to modern recycling, the transformation completes. We've learned that some materials are too valuable to discard, too dangerous to mishandle, and too useful to abandon. Lead will never be green, but it might be the perfect example of circular economy functioning through market forces. That heavy metal under your hood has been serving humanity for millennia. It'll still be serving our descendants centuries from now, because lead never truly dies. It just waits to be reborn.
Every second, 32 tires begin service worldwide. Each survives 100,000 miles of punishment, heat, friction, road impacts before replacement. Picture mountains of rubber growing daily. 2 billion tires manufactured annually, weighing 25 million tons combined. That's every car, truck, aircraft, and bicycle on Earth demanding fresh rubber constantly. How does liquid petroleum become indestructible black donuts? Why do old tires refuse to decompose for 500 years? Stick around. You'll discover the shocking chemical process transforming oil into immortal rubber, and the jaw-dropping secret of where 85% of American-worn tires end up. Hint? It's beneath your feet on football fields.
The story begins in Southeast Asian plantations, where rubber trees grow in geometric rows, stretching miles. Workers cut V-shaped grooves into bark, collecting milky latex sap in cups. Each tree produces 2 ounces daily, barely enough to fill shot glasses. Natural rubber comprises 30% of modern tires. The remainder uses synthetic alternatives derived from petroleum. Massive chemical plants crack crude oil into monomers, butadiene, styrene, then polymerize them into synthetic rubber matching natural properties. These facilities process 50,000 barrels daily, transforming black liquid into white crumb rubber. The similarity is uncanny. Petroleum-based rubber exhibits elasticity, strength, and durability rivaling million-year-old tree evolution. Chemistry replicates nature in months.
Next comes compounding, the secret sauce where rubber meets additives. Industrial mixers, standing 2 stories tall with rotors spinning at 80 RPM, blend rubber with carbon black, silica, sulfur, accelerators, and antioxidants. Carbon black, basically controlled soot production, reinforces rubber while providing characteristic black color. Without it, tires would be translucent white and fail within miles. Each tire compound contains 15 ingredients mixed in precise ratios. Tread rubber emphasizes durability. Sidewall rubber prioritizes flexibility. Inner liner uses butyl rubber for air retention. Formulations remain trade secrets. Michelin's compounds differ from Goodyear's, creating performance variations. Mixing takes 12 minutes at temperatures reaching 300 degrees Fahrenheit. The batch, weighing 500 pounds, emerges as uniform black mass ready for shaping.
Giant extruders force hot rubber through dies, creating continuous strips of tread, sidewalls, and bead filler. These machines operate like industrial Play-Doh shapers, pushing material through shaped openings at forces exceeding 2,000 psi. Tread emerges with grooves preformed. Sidewalls arrive as smooth sheets. Cooling conveyors solidify the profiles. Meanwhile, calendaring machines squeeze rubber sheets to precise thickness, measured in thousands of inches, coating steel cord and fabric plies. These textile layers provide structural strength. Modern radial tires contain steel belts running at 0 degrees to rotation direction, fabric plies at 90 degrees, creating cross-brace architecture. Workers cut these components into precise lengths, stockpiling thousands of parts daily for assembly lines demanding continuous supply.
Comes tire building, robotic ballet assembling 30 components into recognizable shapes. Cylindrical drums rotate while automated arms apply inner liner, body plies, steel belts, sidewalls, and tread in programmed sequence. Each component positions within 0.05-inch tolerance. Precision matters because imbalance at highway speeds creates dangerous vibrations. The green tire, uncured assembly, looks puffy and pale, lacking final tread pattern. Steel beads, wire bundles coated in rubber, anchor edges, providing mounting surfaces for wheel rims. These beads contain piano wire strength steel wound in continuous loops. Braking beads requires forces exceeding 5 tons, ensuring tires never separate from rims even during blowouts. Assembly takes 3 minutes per tire on modern automated lines, producing 2,000 tires daily.
Curing transforms green tires into finished products through heat, pressure, and chemistry. Massive presses, resembling medieval iron maidens, close around green tires. Internal bladders inflate with superheated steam at 350 degrees Fahrenheit and 200 psi. External mold segments, engraved with tread patterns, press inward simultaneously. This step is critical. Vulcanization.
Sulfur atoms cross-link rubber polymer chains, creating three-dimensional molecular networks. Picture chain-link fences welded together at every intersection. That's vulcanized rubber at molecular level. The process, discovered accidentally by Charles Goodyear in 1839, transformed useless sticky material into engineering marvel. Curing takes 12 minutes. Afterward, tires emerge rigid with crisp tread patterns and permanent shape. They'll never soften or melt again. Vulcanization is irreversible.
After curing, quality control begins. X-ray machines scan internal structure, detecting steel belt misalignment, air pockets, or ply separations invisible externally. Uniformity machines spin tires at highway speeds, measuring force variations. Even 0.5-pound imbalance causes rejection. Ship tires must perform flawlessly at 120 miles per hour for tens of thousands of miles. Inspectors examine tread depth, sidewall finish, bead seating. DOT codes stamped into sidewalls identify manufacturing plant, date, batch number, critical for recalls. Modern tires undergo durability testing. Machines simulate 50,000 miles in 72 hours, cycling through temperature extremes, overloading, underinflation. Failure rate must stay below 0.1%. That's one defective tire per 1,000, because tire failure at highway speeds kills people.
Performance testing pushes limits beyond consumer use. Test drivers race prototype tires on proving grounds, executing emergency maneuvers, sustained high-speed runs, extreme weather conditions. Sensors measure temperatures, pressures, wear rates. Data feeds computer simulations refining compounds in construction. Winter tires use softer compounds, remaining flexible below freezing. Summer tires employ harder rubber, resisting heat degradation. All-season compromises performance for year-round versatility. Racing slicks sacrifice tread patterns for maximum contact area. Professional race tires last 200 miles but provide grip exceeding street tires tenfold. Tire engineering optimizes contradictory requirements: durability versus performance, comfort versus handling, cost versus longevity. Every design represents compromises, balancing physics against economics.
This technology evolved from crude beginnings. Ancient Mesoamericans harvested rubber for balls and waterproofing 3,000 years ago, but material degraded rapidly. Charles Goodyear's 1839 vulcanization discovery changed everything. Accidentally dropping rubber sulfur mixture on hot stove created heat-stable material. The pneumatic tire emerged in 1888 when John Dunlop invented air-filled rubber tires for his son's tricycle. That innovation enabled automobile revolution. Cars needed shock absorption only inflatable rubber provided. Radial tire construction, invented by Michelin in 1946, improved durability 50% over bias ply designs. Today's run-flat tires, self-sealing compounds, and airless prototypes continue evolution. Annual global production exceeds 2 billion units, creating waste management crisis demanding solutions. Carbon emissions drop by 62% using recycled tire crumb versus virgin rubber production. Industry saves over $41 billion annually through tire recycling. Processing old tires into crumb costs 70% less than manufacturing new rubber from petroleum. So here's the secret. 85% of American-worn tires avoid landfills through recycling programs. Shredders reduce tires to fingernail-sized crumb. This material becomes artificial turf infill, those black granules beneath football field grass that cushion impacts and improve drainage. Schools, parks, and stadiums nationwide walk on recycled tires daily without knowing. Crumb rubber also creates playground surfaces, running tracks, asphalt modifiers, improving road durability 20%. From petroleum to pavement to playing fields,
cycle completes. Tires never die. They transform. That indestructible black donut refusing decomposition becomes humanity's accidental gift to circular economy. We've learned that immortal materials demand eternal responsibility.
More than half of Earth's entire weight is iron, 32% of the planet's mass. Earth's core is a gigantic ball of molten iron the size of the moon. But iron rules on the surface too. Every second, humanity produces 60 tons of steel, 2 billion tons per year. That's more than all other metals combined. 95% of all metal used by civilization is iron and steel. Without iron, there'd be no skyscrapers, bridges, ships, cars, or trains. How do fiery rivers of molten metal at 3,600 degrees emerge from red ore in city-sized quarries? You'll see explosions in quarries, blast furnaces as tall as 30-story buildings, converters where oxygen turns pig iron into steel in minutes, and rolling mills where 1,000-ton slabs get rolled into paper-thin sheets. Watch to the end. The finale shows why iron holds the world together. This is the story of the metal that built civilization.
The Lebedensky quarry in Russia is one of the planet's largest iron ore quarries. Depth, nearly 2,000 feet. Width, 3 miles. From the edge, you can't see the bottom. A gigantic wound in the earth from which 100,000 tons of iron ore are extracted daily. Excavators as tall as 10-story buildings scoop rock with buckets holding 1,800 cubic feet. One bucket is like a small house. Dump trucks with 360-ton capacity haul ore up the spiral road. Wheels taller than a person. But before loading the ore, it needs to be blasted. Drilling rigs create holes 65 feet deep. Tons of ammonium nitrate explosive are packed into these holes. The explosion? Earth trembles. A wall of rock tall as a skyscraper crashes down. A dust cloud rises 3,000 feet. After the dust settles, excavators begin work. The ore is reddish-brown, sometimes almost black. Magnetite and hematite, iron oxides. Iron content ranges from 30 to 60%. The rest is waste rock. The ore goes to a processing plant. Massive cone crushers grind bus-sized chunks. The noise can be heard for miles. Ore gets crushed to fist size, then to gravel, then smaller. It enters ball mills, steel drums 20 feet in diameter, 33 feet long. Inside are hundreds of tons of steel balls. The drum rotates, balls drop, grinding ore into fine powder. After 8 hours of grinding, you get reddish-brown dust. It's mixed with water, creating pulp, liquid slurry. This slurry passes through magnetic separators. Magnetite sticks to magnetic drums. Waste rock washes away. The concentrate contains 65 to 70% iron. From this, they make pellets, granules the size of walnuts. Wet concentrate gets rolled into balls on special drums, then fired at 2,400 degrees Fahrenheit. Pellets harden, becoming rock solid. These pellets are raw material for blast furnaces. Each plant produces millions of tons of pellets yearly. They're loaded onto trains and shipped to steel mills. A blast furnace is a steel tower 330 feet tall, 46 feet in diameter. 30 stories of pure metal and fire. Lined inside with 3-foot-thick fireproof brick. Internal volume, 176,000 cubic feet. Iron ore pellets, coke, and fluxes like limestone or dolomite are loaded from the top, in layers, like a layered cake. Several hundred tons at a time. From below, through tuyères, openings in the walls, hot air is blown in. Air temperature, 2,200 degrees Fahrenheit. Pressure, 4 atmospheres. Coke ignites. Temperature in the furnace's lower section reaches 3,600 degrees Fahrenheit. Pellets slowly descend, heating up. Different reactions occur at different heights.
First, moisture leaves the ore. Then, at 930 degrees, iron oxide reduction begins. Carbon from coke strips away oxygen. At 1800 degrees, ore becomes spongy iron. At 2700 degrees, iron melts. Drops of molten metal flow down. At the furnace bottom, molten pig iron accumulates, an iron alloy with 4% carbon. Pig iron temperature at the furnace bottom is 2700 degrees Fahrenheit. It glows blindingly white with an orange tint. Pig iron is denser than slag, so it stays at the bottom. Slag, molten impurities and fluxes, floats on top. Every 4 hours, they open the tap hole, an opening in the furnace's sidewall. Pig iron tapping is a fire show. A stream of molten metal flows down channels. Sparks fly dozens of feet. The brightness requires dark glasses to watch. Pig iron flows into massive ladles on railroad cars. One ladle holds 300 tons. It's a locomotive made of molten metal. The ladle gets covered to prevent cooling and shipped to the steelmaking shop. One blast furnace operates continuously for years. Stopping is catastrophic. Metal would solidify inside. The furnace produces 10,000 tons of pig iron daily. That's like 100 railroad cars. Major steel mills have 10 to 15 blast furnaces. But pig iron isn't steel yet. It's brittle due to high carbon content. Steel is needed, an alloy with less than 2% carbon. Pig iron gets poured into a converter, a massive pear-shaped vessel 33 feet tall, lined with fireproof brick. It holds 350 tons of molten metal. The converter tilts, pig iron pours in, steel scrap is added for cooling. The converter returns to vertical position. An oxygen lance, a tube 20 inches in diameter, lowers from above. Oxygen flow begins. A jet of pure oxygen at 150 pounds per square inch pressure strikes the molten metal. Violent reaction begins. Oxygen oxidizes carbon, silicon, manganese, impurities in pig iron. These exothermic reactions release enormous heat. Temperature rockets to 3,200 degrees Fahrenheit. Metal boils and churns. Flame tongues several feet high shoot from the converter mouth. Sparks and molten drops fly everywhere. The blowing process takes 20 minutes. In this time, 350 tons of pig iron become steel. Carbon burns down to 1% or less. The converter tilts, steel pours into a ladle. The molten metal glows blindingly white at 2,900 degrees Fahrenheit. Alloying elements get added to the ladle: manganese, chromium, nickel, molybdenum, depending on the steel grade needed. They mix it by blowing argon through. Then steel gets cast. There are two methods. First, continuous casting. Molten metal pours into a crystallizer, a water-cooled copper mold. Below, a solidifying blank emerges, a slab 8 inches thick, 6.5 feet wide. It glows red, surface temperature around 1,800 degrees Fahrenheit. Gas cutters slice the slab into 33-foot lengths. One slab weighs 25 tons. Second method, casting into ingot molds. Steel forms. This creates ingots up to 50 tons. These ingots and slabs are semi-finished products. They go to rolling mills. There begins the final transformation, turning thick blanks into thin sheets, rails, or beams. Slabs heat in reheating furnaces to 2,200 degrees Fahrenheit, red hot. Then they go to the rolling mill. It's a line of dozens of rolls. Steel cylinders 3 feet in diameter weighing dozens of tons. Rolls rotate toward each other. The red-hot slab enters between rolls. They squeeze and roll it. The slab gets thinner and longer. It passes through the next pair of rolls. Even thinner. Dozens of times. An 8-inch thick slab becomes a sheet 1 to 2 millimeters thick. Length grows from 33 feet to over half a mile. Rolling speed on finishing mills reaches 50 miles per hour. Red-hot steel ribbon flies through the mill, sparks flying everywhere.
temperature drops to 1400 degrees Fahrenheit, metal darkens. The strip cools with water, winds into giant coils weighing 20 to 30 tons. This is hot-rolled steel, the foundation for car bodies, appliance housings, building structures. Global steel production is 2 billion tons yearly. China produces over 1 billion tons, half the world's output. India, Japan, the US, Russia are other major producers. Steel is infrastructure's backbone. 95% of metal structures are steel, from skyscrapers to tin cans, from tankers to paper clips. Iron and steel are civilization's skeleton. Iron is the oldest metal after copper and bronze. The Iron Age began 3,000 years ago. First, iron came from meteorites, ready-made metal fallen from the sky. Egyptian pharaoh Tutankhamun was buried with a meteorite iron dagger. Smelting iron from ore was learned by Hittites in Asia Minor around 1200 BC. They kept the secret for centuries, but technology spread. Iron weapons were stronger than bronze. Iron plows worked soil better than wooden ones. Civilizations with iron defeated civilizations without iron. Medieval times, iron was made in small furnaces. The Industrial Revolution began with blast furnace invention in the 18th century. Early furnaces used charcoal. Later, they switched to coke from coal. The 19th century brought the converter process, rapid pig iron to steel conversion. Bessemer, Martin, Thomas, names that changed the world. The 20th century was steel century. Skyscrapers, bridges, ships, automobiles. Without steel, there'd be no modern world. And so, traveling from explosions in 2,000-foot-deep quarries through giant crushers and magnetic separators, through 300-foot-tall blast furnaces at 3,600 degrees and converters where oxygen burns out carbon in 20 minutes, through rolling mills where 8-inch slabs become millimeter-thin sheets, steel emerges, the metal that built civilization. 2 billion tons per year. 60 tons every second. The metal everything around us is made from. Every skyscraper, every bridge, every car, every ship. It's iron, mined from red ore, remelted in fire, rolled into sheets. More than half of Earth's weight is iron. The planet's core is molten metal. And on the surface, iron rules. 95% of all metal is iron and steel. From nails to bridges, from paper clips to skyscrapers, iron holds the world together. Without iron, humanity would collapse back to the Stone Age. No machines, no electricity, no internet. Everything's built on iron. From fiery rivers of molten pig iron in blast furnaces to steel beams holding up skyscrapers, iron is the foundation, the base, civilization's skeleton. Metal of the gods that became metal of the masses. The most abundant, most important, most irreplaceable. Iron, the metal that holds the planet together. Every day, somewhere in China, a machine generates force equivalent to stacking 200 fully loaded aircraft carriers vertically. This hydraulic press, rated at 80,000 tons, stands 10 stories tall and weighs more than the Eiffel Tower. Picture this. Under its ram, 300-ton steel billets, weight of 60 elephants, flatten like modeling clay in seconds. The ground shakes for miles when it operates. Windows rattle in villages 8 miles distant. How does humanity create machines powerful enough to reshape mountains of metal? Why did Cold War superpowers race to build ever larger presses? Stick around till the end. You'll discover the jaw-dropping reason these monster machines dominate aerospace and defense, the shocking physics of what happens when 80,000 tons compress glowing steel, and why welding became obsolete for the world's most critical components. The story begins at China Erzong Group in Deyang, Sichuan Province, home to the world's most powerful forging press. This colossal machine, commissioned in 2013,
towers 120 feet tall. Picture a 12-story building dedicated to squashing metal. The press frame alone weighs 22,000 tons, constructed from steel beams thicker than telephone poles, bolted together with fasteners weighing 500 pounds each. The facility consumes electricity equivalent to 40,000 homes during operation. 8 separate hydraulic power units, each the size of shipping containers, pump oil through pipes 16 inches in diameter. These hydraulic systems generate pressures reaching 10,000 psi, enough to blast water through concrete like tissue paper. When all systems activate simultaneously, the combined oil flow measures 3,000 gallons per minute. That's emptying a backyard swimming pool every 10 minutes continuously through hydraulic cylinders generating incomprehensible force. Next comes the press bed, a foundation descending 60 feet below ground level, deeper than 6-story buildings are tall. This isn't merely concrete, it's a geological anchor. Engineers excavated solid bedrock, then poured 8,000 cubic yards of reinforced concrete mixed with steel rebar, forming 3-dimensional cages. The foundation weighs 45,000 tons, more than 4 nuclear submarines combined. Why such extreme engineering? Because when 80,000 tons of force compress metal, Newton's third law demands equal reaction force pushing downward. Without this massive foundation, the press would crack bedrock and sink into earth like a nail hammered into butter. Seismographs detect vibrations from press operations 12 miles away, not from noise, but from actual ground displacement. The Chinese government prohibited residential construction within 2-mile radius specifically because repeated press cycles could damage building foundations through accumulated seismic stress over years. Giant overhead cranes, rated at 600 tons capacity and spanning widths exceeding football field lengths, position workpieces beneath the ram. These cranes represent engineering marvels themselves, structures where every rivet matters because failure means dropping cargo worth millions. Control rooms, protected by 18-inch thick reinforced concrete walls and bulletproof glass windows, house operators controlling machinery from safe distances. The press ram, the actual crushing surface, measures 40 feet by 30 feet, larger than most studio apartments. Made from tool steel hardened to withstand pressures that would pulverize normal steel, this ram surface gets replaced every 18 months despite costing $2 million. Replacing it requires 3 weeks of round-the-clock work using specialized welding techniques and stress relief treatments. Even with hardened steel, repeated impacts against 300-ton billets create microscopic cracks propagating until failure becomes inevitable. Now comes forging, industrial violence at physics-defying scales. Workers heat steel billets to 2,400 degrees Fahrenheit in furnaces consuming natural gas at rates measured in tons per hour. At these temperatures, steel glows brilliant orange and becomes plastic, deformable under pressure but not liquid. Picture clay that weighs more than locomotives and requires forces exceeding aircraft carrier displacement to reshape. Overhead cranes lower glowing billets onto the press bed with precision measured in inches, despite handling weights where inches of error cause catastrophic collisions. The ram descends at speeds reaching 20 inches per minute. Sounds slow until you realize 80,000 tons moving at any speed generates momentum requiring precise hydraulic control. One malfunction, one stuck valve, one pressure spike, and the ram becomes an uncontrollable projectile carrying enough energy to demolish the entire facility. The compression itself defies description. As the ram contacts glowing steel, metal begins flowing, literally flowing despite being solid. Under 80,000 tons of pressure, crystal structures collapse and reorganize. Grains elongate perpendicular to compression direction, creating oriented microstructures impossible to achieve through casting. The billet spreads outward, metal squeezing into die cavities with force sufficient to emboss detail smaller than human hair thickness.
This step is critical because forging aligns crystal boundaries, eliminates porosity, and creates grain flow patterns following component geometry. Cast parts contain random crystal orientations and microscopic voids. Forged parts exhibit continuous crystal structures and zero internal defects. That's the difference between components failing under stress versus components exceeding design specifications. Hydraulic systems monitor pressure continuously. Deviations exceeding 1% trigger automatic shutdown, because overpressure shatters dies costing millions, while underpressure produces weak forgings requiring scrapping. After initial compression, the workpiece requires reheating and multiple press cycles. Large forgings need 20 to 40 separate compressions, each reshaping metal incrementally. Between cycles, manipulators, robotic arms capable of rotating 300-ton workpieces, reposition the forging. These manipulators exert forces exceeding 500 tons merely to rotate incandescent metal safely. Picture this: the forging process for a single large component spans 2 weeks. Workers cycle the workpiece between furnace and press 40 times, gradually transforming a rectangular billet into complex shapes: bulkheads for aircraft fuselages, rocket motor casings, pressure vessel heads. Each press cycle compresses the forging 3 to 6 inches, permanently deforming metal through controlled violence. Temperature control matters critically. Too hot, metal oxidizes excessively. Too cold, it cracks under pressure. Operators monitor color constantly, making decisions affecting millions in material value based on visual assessment of orange to red glow transitions.
Quality control begins before forging even starts. Ultrasonic inspection systems scan billets, searching for internal defects invisible to naked eyes. Even microscopic inclusions, slag particles, oxide stringers, sulfide formations, become stress concentrators, causing catastrophic failure in finished components. Rejected billets return to steel mills for remelting. After forging, dimensional inspection using laser scanning creates three-dimensional models accurate to thousands of inches across components 30 feet long. Metallurgical testing cuts samples from forging edges, examining grain structure through electron microscopy. Grain size, orientation, boundary spacing, all must meet specifications tighter than semiconductor manufacturing tolerances. Modern aerospace forgings require grain sizes smaller than 0.005 inches, with elongation ratios exceeding 10 to 1. Without precise microstructure control, components fail unpredictably during service, potentially causing catastrophic accidents. This technology race began during Cold War paranoia. In 1955, the Soviet Union commissioned a 75,000-ton press at Novokramatorsk specifically for forging submarine hulls and missile casings. American intelligence discovered this capability through spy satellite photographs showing the massive building housing it. President Eisenhower immediately authorized construction of matching presses. The Air Force Heavy Press program built 12 presses between 1956 and 1959, including twin 50,000-ton giants at Alcoa and Wyman Gordon. These presses enabled Boeing 707 and later jumbo jets. Without them, aircraft manufacturers couldn't produce wings large enough. The strategic logic was brutal. Whoever controlled large forging capacity controlled aerospace dominance. Nations without heavy presses bought components from competitors, creating national security vulnerabilities. China entered this arena late but decisively. Their 80,000-ton press, exceeding any Cold War relic, announced intentions clearly: aerospace independence. Today, China produces aircraft landing gear, rocket stages, and turbine components previously imported from America and Russia. The press paid for itself within 5 years through import substitution alone. Carbon emissions drop by 43% when forging replaces welded assembly in aircraft structures, eliminating welding energy and reducing weight through integrated designs.
Industry saves over $32 billion annually through large forgings versus machining components from solid billets, which waste 90% of material as chips. Processing costs drop 61% because one forging operation replaces dozens of machining hours. So here's the secret promised. These monster presses exist because physics favors size. Larger presses forge larger components in single operations, eliminating joints where failures initiate. Every weld introduces heat-affected zones with altered crystal structures becoming crack paths. Every bolted joint adds weight and complexity. Seamless forgings eliminate these vulnerabilities entirely. That's why the Airbus A380's wing ribs come from single forgings. No welds, no joints, just continuous metal flowing across 20-foot spans. From Cold War arms race to commercial aerospace dominance, cycle completes. The 80,000-ton press represents more than manufacturing capability. It's geopolitical leverage. Nations with these machines build aircraft, rockets, submarines independently. Nations without them remain customers, technologically dependent, strategically vulnerable. We've learned that industrial capacity determines global power hierarchies as surely as nuclear arsenals. That press standing in Sichuan doesn't just forge metal, it forges national sovereignty.